So we've talked about the second. We still have 2 base units to cover. The second unit we actually have to define is length. And length is measured in meters. And how is meter defined? Again, I'm going to read off. Meter is the length traversed by light in 1 divided by 299,792,458 of a second. In vacuum, that's right. Now, why such a definition? The first definition of meter was, again, it was a reference to the Earth. It was said, 1/40,000 of the equator's length. But that, as you can imagine, is very hard to measure, actually. The improvement of measurement of length is very rapid, it turns out, because measuring the length between 2 places is actually quite simple. If you have a light source, you put a mirror, you send light, it hits the mirror, it comes back. If you can actually measure the time it takes for this thing to happen, this light source to come back, then you can actually measure the difference, the length difference. So what happened is that for a while, competitive groups were measuring the speed of light, and they were coming up with slightly different answers. And there was a big discussion, and someone realized that the definition of second was so nice. Okay? So these different groups were measuring speed of light, coming with different answers, and what actually turned out was the definition of meter. The definition of second was very good, very precise. The definition of meter was terrible. That's why they were coming up with different answers. So they said, hey, the theory of relativity is based on the assumption that speed of light is constant for all observers. So that's an excellent thing to use. It's a universal law. So let's fix the speed of light to a particular value, and let this be the definition of meter. And it actually solved a lot of problems. Again, if we go to our ileri araştırma lab in physics department, you can get a very precise measurement of meter. Okay, again, 1 part in 10 to the 10. So if you want to actually accurately know how tall you are, How about our third base unit? Let's talk about mass. Mass is defined as kilogram. So you may think all these high-tech things, GPS, lasers I talked about. The definition of mass is terrible. 1 kilogram is the mass of the cylinder at Standard International headquarters at Paris. So there is the standard kilogram. It's an alloy, I think iridium platinum alloy. There are 6 of them. So actually, if you want to do a precise measurement of kilogram, that's the thing you actually have to refer to. And that's terrible. I'm at Ankara. I want to do a very precise mass measurement. Should I go to Paris to compare my kilogram to the standard kilogram? Unfortunately, over the last 100 years, over the 20th century, that definition has not changed. So that actually tells you there is still a lot of things to be done in physics. Physics is by no means complete. There is going to be a big meeting of people who are doing all these precise measurements within a year. There are 5 different proposals to, as far as I know, 5 different proposals to change this definition of kilogram. what we can very precisely measure is the mass of a single atom, like carbon, for example, carbon 12, can be measured very precisely. All right. So the problem with that is that the carbon atom is not very practical. No. There are how many carbon atoms inside your body? 10 to do something, but that something is... How about a mole? Do you remember what a mole was? So it was 10 to 23, which means, you know, a mole is more like 1 kilogram of these things, right? So it's much more than 10 to 26, 10 to 28. So we need a practical unit. We need the kilogram to be defined in terms of some practical method. And it turns out most of these proposals have some way of determining this Avogadro's number. Okay. For example, one of them is creating a perfect sphere, almost a perfect sphere out of silicon atoms. We know the volume of a perfect sphere mathematically, right? And that actually tells you how many atoms there are inside the sphere. We know the mass of one atom, so we can actually do a much more precise measurement of the kilogram. But it's not settled yet. Right now, the kilogram we're going to use actually refers to an object in Paris. That's terrible. Okay. Hopefully, within 10 years, or even maybe when you graduate, we'll have a much better definition of a kilogram. Okay? So that should give you some hope. If you're trying to become a physicist, there's still a lot of room to fill in research. Yes?
So if the kilogram unit will change, mass unit will change, then...
You know, it will be a new definition of the kilogram. So it's going to change even at 0.1% level for some measurements, I think.
So the other population of world, they just use the old one.
Yes. So I mean, it's obviously the new unit is going to be as close as possible to the old one. Okay. Good. Let me tell you two more things about how we actually represent numbers. One thing is significant figures. Now, do you think these two representations of my weight, do you think they are equivalent? No. And actually, you intuitively know this. Let me tell you a joke why these two things are not equivalent. Maybe it's not clear, but you intuitively have this notion. So a man goes to the Natural History Museum. There's a very nice Natural History Museum in Çukurambar at MTA, maybe you know. So there's this very nice dinosaur skeleton. He's really impressed, and he asks the guard, "Hey, how old is this dinosaur skeleton?" And the guard says, 65 million and 3 years. The guy is shocked. He says, "How can they know this?" And the guard says, "Well, when I started out 3 years ago as a guard, they told me it was 65 million years old." Okay, so why is this joke funny? Because it actually sees that the guard is not using significant figures. Okay, so saying 65 million years is versus 65 million 3 years. Okay. Obviously, we need a way to express how precise our numbers are. If I actually write the age of a dinosaur as 65 followed by all these zeros, I'm implying that I know all of these numbers. I can accurately measure the age of the dinosaur. So that's not how we're going to write it. What we're going to write is the following. If I'm sure about 65, I'll write it as 6.5 10 to 7 years. Okay? So this is a measurement with two significant figures. Similarly, if I'm really sure about this 3 years also, if I can actually do this determination, then I actually can write it like this, or maybe I can write, nope, 10 to 7 years. And if I keep all these zeros, it means I actually am sure that those zeros are there. Right. So let's go back to my weight. It means if I write it as 83.0, I have 3 significant figures. I'm sure about the 0, but I'm not sure about the next digit. And if I'm writing it as 83 kilograms, maybe, maybe it's 83.7, maybe it's 83.1. I'm not sure about the next digit. So this only has 2 significant figures. Right. Now, how does this practically affect you when you're solving problems? Here is the simple thing. Let's say that I have a area, I have a rectangle which has sides 6 meters by 3.0 meters. What is the area? So Lx is 6 meters, Ly is 3.0 meters. The area is going to be Lx times Ly, 6 times 3.0. Is it 18.0 meters squares? No. What do I need to do? I know that this is 3.0 meters, so I'm sure about that digit, but I don't know that digit in 6 meters. Okay? So I'm not sure about that digit, which means I should not be actually reporting whatever is in the next order. In general, I actually have to be more careful here. How many significant digits do we have in this? This has only 1 significant digit, and this has 2 significant digits. So I have to actually be careful. I have to report this as with 1 significant digit, not 2 significant digits. How would I report this? So should I write 2 10 to 1 meter square? Now, general rule is this. The general rule is that use significant digits which is equal to the minimum significant digits inside your given quantities. Okay? But still, here I know that I will not be. Okay, let's think about this. 3.0 is right. What happens if this is 6 and I'm not sure about the next digit? It can either be 6.0 or it can be 6.9. If I multiply this by 3.0, this is going to give me just 18.00. How about this? This is going to give me, so this is 720.7. So it actually means that this is somewhere between 18 and 20.0. So this is actually, you see, it's actually a better representation of all the possible range. Okay? One more sort of stupid convention. Generally, if significant figures are not expressly given, so in some problems You're just supposed to multiply the numbers and do not care about significant figures. Give at least 2. One thing you should definitely not do, and this is very important for your lab course. What happens if let's say you have found that your toy car went 20 meters within 3 seconds. I would like to find its velocity. So what you do is, okay, I will, oops, not this one. Let's see, where is my calculator? So you open your calculator, you say 20 divided by 3 is, and then you write this, 6.666666667. That's a terrible thing to do, right? Because your calculator actually gave out so many numbers does not mean they actually are significant, okay? What you actually know is that if this is 20.0, there are 3 significant figures. If this is 3.0 seconds, then there are 2 significant figures. You actually have to express with only 2 significant figures. You don't write it like this. You write it as 6.7. You round to the higher integer. If it's above 5, if it's below 5, you know how to do rounding. I'm not going to talk about that. Sorry? If it's 5, you round up. Up. There are different notations. Don't worry about it. Okay?
12.5 is rounded 30.
Sorry?
12.5 is
Rounded 30, yes. So 6.7 meters per second. So if you actually have to give out a numerical answer in your homework, in your exams, in your quizzes, 2 things are extremely important. One is that correct units are used. If you express a numerical answer without units, it's very likely that you'll lose all of your grade for it, even if the number is correct. If you do not give out units, that's actually wrong. Okay, you're going to be scientists. You have to specify everything precisely. You have to give the correct units. The second thing is correct number of significant figures, especially the software which does the checking for your homework is very, very strict about these significant figures. So when you're doing your homework, be careful about reporting your results. Okay? But now, I'll tell you one more thing which I find quite interesting. It's about units again. It's called dimensional analysis. Now, this is going to help us check our answers all the time, and it's going to, in certain cases, help us solve problems without actually knowing what's going on. And I'd like to demonstrate this by one example. So here is a simple problem we're going to solve probably within 2 weeks. If I have a mass m on a table that is rotating with velocity v on a rope of length L, so it's going around in circles with velocity v. It looks like a square, so trying to do a better circle. Okay. The question is, what's the tension in the rope? Okay. Now, obviously, I know many of you can actually solve this problem. You can tell me the answer right outright. But here's what I would like to say. What is the unit for tension? Tension must be a force. Okay. So it must have units of And when I use these square brackets, it means the units. It should be Newton. Now, what is the derived unit Newton in terms of the base units of length, time, and mass? It's kilogram meter per, no, meter per second square. How do I remember this? F equals ma, something we're going to see again. So here is the thing. I believe this answer, my final answer, must be expressed in terms of my given quantities. What are the given quantities? It must be, so let me make this mass capital M, so it's not meters. It must be expressed in terms of M, L, and V, and it must be some multiplication of these, A, B, C. Okay. What is one quantity I can make out of these given quantities so that it has the correct units? That's the question I would like to ask. So M has units of kilogram, so it's kilogram to the A. L has units of meter to the B. V has units of meter per second. So meter to the C divided by second to the C. And that must equal kilogram meter divided by second square. By just comparing these two equations, kilogram to the A, I have only kilogram on the right hand side. A must be 1. Meter is 1. Here I have meter is B plus C. B plus C is 1. I have S second to the C here, second to the square. C is 2, which means B is minus 1. So from here, T must be M to the A, M, B to minus 1, L to minus 1, V to 2, or M V square over L. I did not use Newton's equation. I did not use anything else. So my guess here is that the answer will be mv square over L. For this example, it turns out this is exactly the correct answer. Okay. So that should tell you that dimensional analysis units actually tell us more about nature than just being tools for us to agree on something. Okay. Obviously, the answer could be 5 times mv square over L, or 1 over square root of 2 times mv square over L. But nonetheless, we have a good way of checking or finding the answer just depending on the units. And what we're going to do is every time we solve a problem, we're going to check that it actually has the correct units. All right? You'll see that as I solve more problems. Let me talk about one more thing. Let me talk about order of magnitude estimates. What does that mean? When I write any number in the scientific notation, I could not write scientific, that's great. What was the scientific notation? I'll express any quantity with just one significant figure to the left of the decimal mark, remaining significant figures to the right, and then I'll write 10 to whatever is the power. This power is called the order of magnitude. In many cases, when you're going to do an experiment, for example, you do not really care about the exact value of some parameter. For example, let's do an engineering example. If you want to design an elevator that's going to carry 4 people, you don't really care about everyone's weight. What you want to actually use is an average weight. Maybe you want to also be on the safe side. So what you would say is that, hey, average human weighs 100 kilograms. So order of magnitude is 100 kilograms. Okay. Now, the worst case, it can be actually 10 times larger than that. Maybe it's not a human, but some animal comes into the elevator. The bottom will be 10 times less than that, so it will be just a small child of 10 kilograms walking onto the elevator. But when you're starting out to design, you just start with some average number, and you don't care about what's written in front. You just first care about what's written as the exponent of 10. Okay? Now, in physics, many things will require you to estimate the order of magnitude. Sometimes it's actually very hard to do that. For example, how many stars are there in the Milky Way galaxy? When you actually want to find that number out, you do not really care about the exact number with 35 significant figures. What you actually want to know, are there 1 billion stars, 10 billion stars, 100 billion stars in the Milky Way? How many galaxies are there in the observable universe is another question. Do we have 5, 10 galaxies? Do we have 10 to 25 galaxies? Or do we have somewhere in between? Our estimates right now is it's 10 to 20 or so. Okay? So knowing that order of magnitude, estimating the order of magnitude is an important thing. So if a question actually asks you to estimate a number with an order of magnitude, your final answer may be 10 times lower than the true result. It can be 10 times higher than the correct result. That still be considered correct. It will be a good order of magnitude estimate. Okay? That's what an order of magnitude estimate means. Any questions? Nope. So I think that's basically all I actually want to say about measurement, how we express our results. 2 things that you should definitely remember out of this first chapter is that every number you quote, you write down in your lab, in your exams, in your quizzes, must have a unit attached to it. Unless, of course, it doesn't have any units. Okay. How many students are there in the classroom? 55. You don't have attached a unit to that. Well, we may say students, okay. But if I ask you estimate how much mass there is inside this classroom, biomass, how much biological mass, then what do you need to do? How would you estimate the total weight of this classroom? Again, an order of magnitude estimate. Let's say there are 60 people. Okay. So everyone weighs 100 kilograms. Okay. So, okay, that's not too bad. It's not a bad estimate. Okay. Maybe most of you are more closer to 50 kilograms than 100 kilograms, but that's only a factor of 2. I'm interested in finding the answer up to a factor of 10. So if I'm making an order of magnitude estimate, then what I just care about is what's written on the 10 to the part. All right? Good. So let's talk, now that we've talked about measurement and mechanics, these base units, let's start talking about one-dimensional motion. So what do we mean by one-dimensional motion? It means that I actually have some object which moves. Let's say at time t equals to 0, it's at one marker. At time t equals capital T, it is actually at another marker. Okay. Now, one thing that we are going to certainly use is how much this object has moved during that time. So this is called x is the displacement or position of the object. And actually, at the end of the day, all of our mechanics problems reduce to, in one way or another, calculating where some particle is as a function of time. In certain cases, maybe the problem will just require you to do the reverse. It will give you how the position changes as a function of time. It will not be only one-dimensional. We'll actually look at how objects move in all three dimensions. We'll look at other things like objects not maybe moving, but rotating around themselves. Okay? But that, again, will be not the position, but the angular position of the object. But our central quantity is how our position, x, changes with time. Sometimes this is also called the trajectory of the particle. Okay? Now, that's good. If I say that at time t equals to 0, I am at 0, and at time t equals capital T, I am at x, I can ask the following question. What was my average velocity during that motion? And that's actually intuitively very easy. That's a concept we all know. Eskişehir is 200 kilometers away. I drove to Eskişehir in 2 hours. What was my average speed? 100 kilometers per hour. Okay? So that's very easy. The average velocity, V average, is total displacement divided by t. Okay? Divided by time difference. And why? Let me be a little bit more specific. In general, what we can actually think about is that maybe, let's see if you can see this blue, instead of giving you the displacement, I can put a different coordinate system. X here, we don't need another marker, another axis. At time t equals to 0, my position is x at 0, and at time t equals to t, my position will be x at t. Or even I don't have to start my chronometer exactly at the starting point of my trip. I can say this is time initial. So my initial position will be x at time initial. And this is going to be x time final. T equals t final. I can maybe express this a little bit better. It's my final position minus my initial position divided by the final time minus the initial time. Okay? So this is again extremely intuitive, something you know very well, right? Now, the problem, of course, here is that, for example, if a cop is going to write a ticket to me because of speeding to Eskişehir, he's not really concerned about my average velocity. Okay? 100 kilometers per hour, it turns out, is a legal velocity on the highway in Turkey, right? What he really wants to know is if at any time during my trip I have exceeded 110 kilometers per hour, which is the maximum speed limit on the highway. So we need to define something better. We need to define an instantaneous velocity. And when you're driving a car, you actually know. Your average velocity is probably fixed when you're coming to Bilkent every morning. But your instantaneous velocity will be very different. When you're in a small street, you're driving very slowly. But when you're on the highway, you're actually driving quite fast. So we need to define an instantaneous velocity. And that's how do we do this? Well, so here's what I'll do. I'll actually plot my position as a function of time. Okay, that I said my trajectory is my central quantity. And here is, let's say, that's what it looks like. Now, if this is my initial time, and this is my final time, what is my average velocity? How can I calculate my average velocity? Well, I have a very good definition. My position at initial time is x time initial. My position at final time is x t final. So my average velocity is, this is x t final minus x t initial divided by t final minus t initial. So if I think of the following triangle, if this angle is theta, V average is basically tangent theta. That's 6. Now, how about the instantaneous velocity? How should I do this? Well, instantaneous velocity means I'm making the time difference shorter and shorter. So if I'm actually worried about the instantaneous velocity here at time t, I'll choose a time which is closer to it, t plus delta t, and form the same triangle. Okay. So I'll actually form the same triangle at a very small distance. So what I would like to define as V, and I'll not write instantaneous, that will be my definition of V. I would like to find, and it's going to depend on t, so let's say explicitly. I would like to find the change of my position within a small change in time. So what's this going to be? X of t plus delta t minus x of t divided by, t is cancelled here, delta t. But if I really want this to be instantaneous, I should be taking delta t as small as possible, as small as my instruments allow me. Actually, mathematically, I actually want this delta t to tend towards 0. It will not be exactly 0, but it will go to 0 as a limit. So I'll say limit delta t goes to 0. Hey, but that's excellent. I think maybe you didn't have your first calculus lecture, but I think within a week, your calculus instructor will exactly tell you this concept. It says, hey, if I take delta t to 0, what I'm doing is I'm actually defining the slope of the tangent to this line. Okay? I'm making delta t going to 0. These triangles get closer and closer to my curve. Okay? So I'm looking at the slope of the tangent there. This is exactly the definition of the derivative. The velocity is the derivative of position. Okay? Now, the way I define this, velocity has a sign. If I'm moving to the right on my axis, on my x-axis, velocity is positive. If I'm moving to the left on my axis, velocity is negative. Okay. Because x is increasing means its slope is positive, so velocity is positive. If I'm going the other direction, velocity is negative. So people sometimes, for example, the odometer in your car, the speedometer in your car doesn't know which way you're heading. It tells you the absolute value of your velocity. So it gets another name. This is called speed. So speed and velocity are actually different things. Speed can never be negative. It's always a positive quantity. Okay? Now, I'll talk more about one-dimensional motion on Thursday. And your recitation will be about one-dimensional motion on Thursday. But let's finish today. Let's do our quiz. And I'll see you on Thursday. Okay?